Okay, good morning, everybody. Our Top Hat code for today is going to be 3276, or it is 3276. Okay, you can see my screen. Let's just bring the chat up. Okay, before we embark on today's lecture, our third in a series of 3 lectures on graph algorithms, just a comment or two about assignments. So what we've been doing in a lot of our assignments is doing empirical performance testing, right? How long does it take? So if you get your times are 0 or near 0 for things that should take a long time. So I'm not talking about binary search, which is pretty darn fast, but something that's an n squared or an n cubed algorithm, and you're getting 0 or near 0 for your time, that is a heads up that something is wrong. So one possibility is that your code isn't working, and so you don't run the algorithm. And then it will go very quickly because it's not running. Another possibility is you think it's running and it really isn't. So one thing to look at is, what is the algorithm actually returning? What is it doing? If you're doing something like searching, when we did search together, we ensured that the thing was actually searching, right? We took the index and we compared that to the index that we know is correct. And we said if they're the same, that's great. If not, there's an error message. There should be an error message. If you're doing sorting, you want to test it, right? Make sure that the array really is sorted afterwards. So you can, a very simple 2 lines of code to check if the data is sorted, right? If you're doing matrix multiplication, you can have a check, right? You know what the product is because we can use the NP the multiply using NP, and see, does our simple multiplication, does our Strawson come up with the same answer? If it doesn't, it could be a rounding issue, but we're dealing with integers, so it's probably not a rounding issue. Then we have a problem. So that is, at this point in your, undergraduate studies, you should be familiar with the idea of testing things to make sure they go through. So what I noticed in some cases is people either weren't calling the algorithm, or they were calling an algorithm that didn't do anything. It returned after 1 line, and all that code that was there didn't do anything. So a heads up is if your time is 0. But again, you should be doing some kind of test, very simple test, to make sure that you're getting the right answer. And that is more important than printing out. So, printing out a matrix that's 500 by 500 in your output is not real helpful, because no one knows what to do with that. Whereas if you have 2 lines of code, 3 lines of code that check if it's the right answer, we don't need to print it out. Then we, either we know it's correct, or if there's an error, then we deal with the error, right? So those are just some tips for successful, completion of these assignments, and really anything in life. You always want to have some kind of testing to go on, what we call even a sanity check. All right, so today we're going to start with a concept called minimum spanning tree. We spoke briefly about a spanning tree in a previous lecture. And if we have a graph, in a graph, nodes may be connected to each other in multiple ways. So for example, imagine you have a graph that looks like a square, which happens to be a cycle graph. It also is a regular graph. It looks like a square, 4 vertices in the 4 corners. So I can go from 1 to 2 to 3, and I can also go from 1 to 4 to 3, right? I can go 2 different ways. So the graph doesn't necessarily need to have multiple ways of doing that. So what we look for is a spanning tree. Now, there may be multiple spanning trees. Which spanning tree do we take? We take the one with the total cost that is smallest. That is what we mean by a minimum spanning tree. So if there are multiple spanning trees, sometimes there is only one. If you start with a tree, there's only one spanning tree. But if you have multiple, which one do I use? All right, so just to review again, we have this slide is from a previous lecture, right? A tree is a connected acyclic graph with the number of vertices equal to the number of edges plus 1. All right, acyclic means that it doesn't have a cycle, but if I add even one edge, it now has a cycle. And if I remove an edge, right, it will no longer be connected. The spanning tree says, make sure that I have all the original vertices, but only keep as many edges as I need to ensure connectivities, right? So that will be a tree. And then a minimum spanning tree says, take all the different spanning trees that are there and give me the one with the lowest cost. Now, this is a practical problem, right? It's not just, something some computer scientists came up with because they thought it was interesting. It's a practical problem because if I have a network of utilities, gas, natural gas, oil. Oil is actually usually local, so oil wouldn't be a good example, but natural gas, telephone, internet, right? Water, right? So we need to have all these different things that are connected. All right. How do we do that? And we don't want to have more connectivity than is necessary. We just want to ensure that everything has one way of being connected to the network because piping is expensive. So we want to figure out a way that minimizes those costs. Now, here is a property that both Prim's algorithm and Kruskal's algorithm is going to rely on. And it says as follows, it's called the min-cut property. And it says as follows, if I have two edges that connect two sets of vertices, right? So I have some on the left, some on the right, and I have two edges between them, which one should I choose? Anyone want to guess? And I'll give you a hint. We're going to use a greedy strategy. Everyone see that word on the bottom of the page, bottom of the slide? So if I have two edges between, let's say, one set of vertices on the left, another set on the right, which one do you think I should choose?
Keep the smaller one?
I use the smaller one. That's correct. Okay. The argument is because if I used a bigger one and I put a smaller one in also, I now have a cycle. So obviously that's overkill. So I use the smaller one. Now, that's not entirely correct. Okay. What actually is correct is that using the smallest one will give me one of the minimum spanning trees. Okay, it is possible that there's another way to do it with the larger one that will be equal. So it's possible to have two minimum spanning trees. Okay, so what we're going to do now is we're going to learn two algorithms, one called Prim, one called Kruskal. Both of them solve the minimum spanning tree problem. Both of them are greedy algorithms, but they work a little bit differently and hence they have different names. All right, Prim's algorithm starts with two sets of vertices. One set of vertices is empty. One set of vertices has all the vertices, and gradually we take one vertex and move it from the set on the right, let's say, that had all the vertices to begin with, move it to the left. Now, how do we choose which vertex to take from that set? And the answer is we take the vertex that is closest to something in the first set. So we take something from set 2, S2, that is closest to something in set 1. Now, initially, set 1 doesn't have anything, so it doesn't really matter which one you take. But subsequently, you always take the smallest. That's where the greedy strategy comes in. So here is code for Prim. Okay, this is a Python code. And let's take a look at what it does. So first of all, we create an array of length self.v. What does self.v mean in plain English?
The amount of vertices in the
It's basically times means the size of the number of vertices, right? So what this line does is it says, give me an array or a list where everything is infinity, okay? The size of which will be the number of vertices. Okay, why? Because initially the costs, okay, the keys are basically these costs. The costs are all going to be infinity, right? Because when we start, everything is infinite away. It's going to change pretty quickly. And then we change the key of the starting vertex to have a cost of 0 because we pick something. So we just pick the first one. It doesn't really matter what you pick. but by convention, we just pick the first one. And we also keep track of which ones we've already used. So basically, visited means it's in set 0. The first set, and not visited means in the second set. So as we move vertices over from set 2 to set 1, we mark them as visited. All right, so we iterate over the vertices, okay? So basically this is a loop. We iterate over the number of vertices, and we find the min, the smallest in that list. Where have we done something like that before? Which algorithm did we do something like this, where we took the smallest key and we used it? I'll give you a hint. It was very recent. And I'll give you another hint. We used 3 different data structures for this concept. So, meaning 3 different choices, each one better than the previous one. So the answer is it was Dijkstra's algorithm, and the 3 choices were: first we used an array and found the minimum of the array. Then we used a regular min heap, kind you learn about in data structures. And that went down, instead of order n for finding the min, it went down to order of log n for finding the min and restoring the heap. And then we did talk briefly about something called a Fibonacci heap, where it was also log n or log v, the difference being that the updates, subsequent updates in the next few lines, went a little bit faster. Okay, so we find the min, the closest vertex, and we call that u. And then we mark u as visited because it's now in the set on the left, the S1 set. And we look at all the vertices and we say, okay, what does this first condition mean? What did I say about this first condition? Everyone see my mouse?
You can't have any negative cycles.
No, that's not about negative cycles. No, you're right. We don't want negative cycles, but that's not what that's about. So remember, I told you that you always have to look at code. If you're getting code online, Geeks for Geeks, but any code online, you have to understand how are they representing the graph. What happens if the edge doesn't exist? Do they put infinity there or 0? So Geeks for Geeks tends to use, and again, not all their code is consistent because it's written by different people. So Geeks for Geeks generally uses 0 for a non-existent edge. So this is saying if the edge exists, that's what this line is, this expression here is saying. If the edge exists and that vertex had not yet been visited, right? So it's still false, has not been moved from set 2 to set 1, then we check and we say if, right? This is the update part, right? These lines are the update part. So it's saying if I can go from u to v in less than the current cost to v, then going from u to v is a better way of getting from u to v, u being in the first set, v being in the second set. And so we update that, right? So we're going to analyze this algorithm for time complexity and different choices. But before we do that, it's helpful to trace it. Okay, you may recognize this graph. You know where we had this graph? We had this graph in a previous lecture in Dijkstra's algorithm. All right. Now, what you may notice that I've done, and I admit I did a pretty bad job of it. Anyone see what I did? It looks like you can see my bad Photoshop. What did I do to the picture from last time?
Erase the arrows.
I erased the arrows. All right, so it's a deliberately bad, I don't know if it's deliberately bad job. That's giving myself too much credit. But it's a bad job, but it helps bring to your attention that I don't want the arrows there, right? So I erased them so well that it doesn't look like a line anymore. All right, okay, because minimum spanning trees work on undirected graphs. I'm not saying you can never have such a problem, but the classic minimum spanning tree problem is for an undirected graph. So I'm using the same graph as before without the direction on the edges. So here we have a trace, okay? The table will even look a little bit like the trace I had in the, sorry, I'm gonna close my chat for now. All right, so what are we doing? Okay, we pick one vertex and all the other vertices are in S2. And what happened now? Well, we look at the cost of going from 1 to everything else. So the cost of going from 1 to 2 is 2. The cost of going from 1 to 3, 3 is over here on the right-hand side, right? I'm sorry, it's not on the right-hand side, it's on the left-hand side. So the cost of that is 4. The cost of going from 1 to 4 is 1. Cost of going to 5, 6, or 7 is still infinity. Okay, so which one of these is going to be chosen when I need to pick the min? Which of these is the smallest? Which is the smallest?
Vertex 4.
That's correct. Sorry. Vertex 4. So I'm putting a little line there to indicate that it has now been visited and I need to update. So let's just look at which ones. A lot of things are getting updated here. So 2 didn't change, but 3 did. Why? Because now I can go from 1 to 3 with the cost of, I said 2 there. Is that a mistake?
Is it 3?
Yeah, I'm just wondering, did I make a mistake there? Or sometimes I'm just not looking at it right. So again, this is the cost of going from 1 to,
You can go from 1 to 2 and 2. That should be 3.
no, so I'm going from 1 to 2 in 2. But the question is, what about going from 1 to 3? Oh, no. It's not going from 1 to 3, okay? This is not Dijkstra's algorithm. This is Prim's algorithm. It's a cost of going from something in S1 to vertex 3. So what do I have? I have 1 and 4. So I can go from 4 to 3 and 2. Everyone see that? So it's not Dijkstra's algorithm. This is not the source. There's no concept of a source here. What we're doing is we're going from S1 to S2. So I can go from 4 to 3 with a cost of 2, and that's what happens here. I can go from 4 to 5 with a cost of 2. I can go from 4 to 6 with a cost of 8. I can go from 4 to 7 with a cost of 4. Right? Which one am I going to choose next? So of all of these, which is the smallest?
2, 3, or 5.
So I have 3 choices. Which one do I do? I just picked the smallest one. All
So
right.
what about the vertex 2? Seems like it goes from 1 to 2. Is that the case?
It's saying, yeah, because I can go from either one of these to each of these, right?
So just
I can
choose the
go from
minimum.
1 to
right?
2 with a cost of 2,
Okay, got it.
right? So now 2 becomes part of set 1. And which ones get updated? None of them got updated. So there's nothing to do there. Then I choose one of these 2s. So I'm using the 3. You generally pick the smaller vertex if there's a tie. And this one changed. Why did this one change? Because I can go from 3 to 6 with a cost of 5, which is better than going from 4 to 6 with a cost of 8. You get the idea? Then I choose this 2, nothing changes. When I add over here, I've added 7, so I can go from 7 to 6 with a cost of 1. And that one gets chosen at the bottom, right? So that's the idea of Prim's algorithm, all right? Again, one important distinction between Prim and Dijkstra, aside from the fact they're solving different problems, is, well, precisely because they're solving different problems. It's not about the source, right? It's not about how do I get from vertex 1 or vertex 0 to every other vertex. That's Dijkstra's algorithm. This is about spanning. This is about connectivity. So it's saying, take the vertex I just added and see if that is closer to one of the vertices in the other set better than whatever I had before. So this is what I'm left with, right? If I look at all the, the connections actually use, this is the spanning tree, which is also a minimum spanning tree. And, you could also talk about the total cost, right? So it's going to be 2 plus 1 plus 2 is 5 plus 2 is 7 plus 5 is 12. Okay, so how do we implement this, all right? So one choice is to use an adjacency matrix. And to find the min, I basically look at all edges. I look at all edges and their costs. And then I need to do that V times, so that's V cubed. Now that's a really bad option, right? The second option is a little better, much better, actually. We take our same adjacency matrix, but this time we have an array, a helper array, and we gave that helper array a name. In our code, the helper array is called key. So we initialize it to all infinity. And in our picture, we effectively have that too, right? This row here is effectively called key, right? So what we're doing is we look through the array. How long does it take to find the min of an array? Let's look at the code again, right? How long does it take? If key is an array, how long does it take to find the minimum?
V squared.
Well, no, to find the minimum of an
V.
array is what? V, right? Or N, number of items in the list, in the array, right? Okay, then we need to update that. Well, the update is a loop over V. Okay, so we have V for the min, okay, even though it looks like one line, but it's really OV. And then we have the updates, so that's at most V. And so it's V plus V, but I need to do that V times over the course of the algorithm, so that's where that V squared comes from. Okay, so the find min is V, the update is V, but I'm doing that V times. Okay, if you want, I could write it like this. So I could say like this, I could say it's V times O of V squared equals O of V cubed. Okay, and this time it's V times O of V plus V equals O of V squared, which is equal to O of V squared. Okay, then we have this one here. All right, so this, anyone remember from Fibonacci, this is for what? There are two primary actions here. One of them is finding the min, and one is the update. So anyone remember which is which? It's the same as what we saw last time. So I need to find the min. The min costs log of V to do the min. I need to do that V times, right? So that's the V log V. This is finding the min V times, and this is doing the updates, because I could potentially have to update one per edge. Okay, so that's where the E log V comes from, for a total of E log V, assuming that E is bigger than V, which it almost always is. And finally, we had the adjacency table. So in the adjacency table, this is the cost for finding the min V times, and this is the amortized cost of doing the update. So we said that the amortized cost per update is constant time. Multiply that by E is basically E. All right, so these are four options. Again, the first option is really so bad, I didn't even call it option 1. I called it option 0. And we had the same concepts back in the previous, in the lecture on Fibonacci. Anyone have any questions on that? Okay. So our other algorithm that we're going to study for minimum spanning trees is something called Kruskal's minimum spanning tree algorithm. It is also greedy, but instead of focusing on the closest vertex, its focus is on the smallest edge. So what we do is as follows. We initially put each vertex into its own little group. Okay, so we call that those groups sets, and we call the operation to put them in a group, we call it a make set. And what we do is, in a loop, we take the next edge from the list of edges that are sorted. All right, so they have been sorted. Excuse me. They've been sorted. We take the next edge from the list and we say, if the edge is between two different groups, two different sets, two different components, then we use that edge to combine the components. If they are in separate components, I'm sorry, if they're in the same component, you need the edge because we already have connectivity. And we keep on doing that until we have V-1 edges, right? Let's take a look at this code. This code is also some Python code. All right, so we have some initial variables here, but this is the first important piece. What this does is it creates a separate little unit for each node. Okay, so we're creating units of separate nodes. And here's what we do. We sort the edges. Anyone see? Here it is. Okay, so here we're sorting the edges by item 2. Now, what is item 2? That's not necessarily obvious. It's saying sort by the edge weight. Okay, so there are actually 3 pieces to item. Item has the start vertex, the end vertex, and the weight, right? So you need 3 things in an edge. So item of 2 is a third of those 3 things. It's saying this line here is saying sort by weight, sort by weight. All right. So what we do is we take the next edge out of the list of edges and we find which group each of the 2 vertices belongs to. Got a slight typo there. All right. And I say if they are not in the same group, right? That's what this is saying here. If they're not in the same group, right, they belong to different groups, then use that edge. So add 1 to the number of edges that we have so far and add that edge between U and V in. So that is the basic idea of Kruskal's algorithm. And let's sort of walk through it together. All right, so we have the same graph we had before. Notice that the graph is also undirected, just like it was before, right? So there should not be any arrows on the edges. Again, I did a sloppy job of cleaning it up. And we sort the edges in increasing or decreasing order.
Increasing order.
Increasing order. Good. Now, keep in mind that there could be ties, and we'll deal with that. Okay, so which edge am I going to use first? Hint, this is a greedy algorithm.
Lowest weight.
Lowest weight, lowest cost. So I'm going to use edge 6, 7. And I say to myself, are they in different groups? Okay, oh, I actually map it out here. So look at that, right? So initially, each vertex is in a separate group, right? That's the number of the group. So 1 is in set 1, 2 is in set 2, and so on, right? So I took the smallest edge, it has a cost of 1, and I combine those 2 vertices into one group. Then I take the next smallest edge. The next smallest edge was 1, 4. 1 and 4 are currently in separate groups, so I combine them, right? So first I need to do find. Find means find what group it belongs to. This belongs to group 1. This belongs to group 4, and I combine them. We call that union, and they are now in the same group. And I take the next smallest edge. The next smallest edge is 1, 2 for a cost of 2. 1 is in group 1, 2 is in group 2, and I combine them. Then I take group 4, edge 4, 5. 4, 5 has a cost of 2. 4 is in group 1. 5 is in group 5, so I combine them. Then I take 3, 4. Just move this guy out of the way, sorry. All right, I take 4, I did that one. I take 3, 4. 3 and 4 was I combine those, and finally I take edge 4, 7, and 4 is here, and 7 is there, so they get combined, and they're all together. So I just have everything in one group. All right. So that's Kruskal's algorithm. Now, as before, the challenge is going to be to figure out how we implement these 3 operations. So I want you to go back to the code for a second. And there are 3 main things here. The first thing is putting each thing in its own group, right? We call that make set. That's the word, the abstract word that we use. And that's what we're doing here, right? We're putting each thing in its own group. That's called make set. Then we have a find operation. Okay, find means find what the U belongs to and find what the V belongs to. So in our trace over here, we're saying over here, okay, find out, right? Oh, 4 belongs to this group And let's say here, 4 belong to this group, 5 belong to that group. So we're going to combine them. So we need to find what they belong to. That's what these two lines are doing. So notice we have to do find twice. One's for the U and one's for the V. And then if they are in different groups, we combine them. So this line here, maybe I'll put that as union. Okay, so everyone see that here? Just change the, call that union. You know what? So here's what I'm going to do. Okay, so let's say this. This is going to be pick the next edge. I'm going to write this a little differently here. So this is pick the next edge. This is check the subset. And then we're going to do combine if different. That's this. That's what this is saying. All right, so here is here are the main 3 operations, okay? And we call these disjoint set operations. If you look in the Xi book, right, there's actually, I think, an entire chapter called union find or disjoint sets or disjoint forests or some disjoint set forests, right? There's an entire chapter that deals with this topic. Okay, so we need to run make set at the beginning. Make set gets executed on each vertex. So that's going to be whatever it takes times V. We're going to need to do find. Now, how often do we do find? Well, we need to do find for every edge, and we need to do it twice, right? Because we do find on one vertex, and we do find on the other vertex. So that's going to take 2 times E. And then the union, we only do union till we build the tree. So the number of edges in a tree is V minus 1. So that's this thing here. So we actually have a lot of options how to implement this, okay? One way is the way that is sort of pictured in here, right? So if I gave you this table and I said code that, right? Code that, what data structure would you use? You'd probably use an array, right? An array of size V. You would probably look at that and say, oh, that's an array, and we keep updating the array. So that's what this first option is. We have an array that keeps track of what set does each thing belong to. And find is very fast, right? Why is find fast? Because for each item, I just look at what is its corresponding representative. So, sorry, going the wrong direction there. So that's actually pretty fast. But union is a pain in the neck because they have to update all the members of the set that's changing. Let me give you an analogy. So let's say Queens College decided that it was going to incorporate Queensborough College into Queens College. Okay, they're going to get rid of the community college. They're just going to move everything into Queens College. Okay, they'll have harder courses, easier courses, but they're going to put it all together. So everyone in the Queensborough system that used to be part of Queensborough is now going to need to get, onboarded. They're going to get sort of, moved into the Queens system. So everyone in that list is going to need to get, let's say, a Queens kind of, maybe not, let's say an ID card and, other things that are specific to Queens College, right? So that's what happens here. The union is more expensive. The union says I have to update all the things that are getting merged into the other set. So the total amount of work is the O of E for the finds, and then the V unions, each of which took V time. So if E plus V squared equals O of V squared. Can someone tell me why E of plus V squared is equal to O V squared? Why is it not O of E? Or why are we able to drop the E?
Since E is dependent on V?
Well, it is dependent, but dependent isn't good enough reason to drop something, right? If
V squared,
say it again.
V squared is the dominating
V squared is dominating. Why is it dominating? Because how many edges can you have? The most edges you could have
Most of
is, it's an undirected graph, would be V times V divided V times V minus 1 divided by 2. So the number of edges at most could be about half of V squared, right? So V squared is dominating. In many cases, it will be much less, but certainly it's a smaller number. All right, so that's why we can drop out in this little thing here, we can drop the V squared. So that's just one implementation, not the best implementation, but a simple implementation. A second choice is a forest. Okay, we have a set of trees that represent these components. So now to find something, we need to navigate the tree. Now, normally when you learn about trees and data structures, even in our course, you start at the top, at the root, and you work your way down until you get to the thing that you want. In this case, we're going backwards or upwards, right? We start at the node that we want and we work our way up to the root. The root is our representative. All right, so how long does it take to get from the bottom of a tree, let's say, to the root? Well, if it's balanced, then it's log of the number of items. But if it's unbalanced, right, there's nothing here that says that it's necessarily balanced, it could take O of V. So that's where this O of V is coming from. But I need to do that twice for every edge. So this comes out to be 2 times EV, and 2 times EV is the same as 2 EV. And I need to do the union. So the union is easy because I just make one tree point to the other tree. So I just make it point to the root. By the way, these are not necessarily binary. So that takes O of 1 times V minus 1. So I have 2 EV. Let me just write it a little more detailed here. So you could say as follows. I have 2 EV plus V minus 1 times 1 equals O of EV. Okay. All right, so that's my next option. Now it's where it starts to get interesting. And we introduce 2 improvements. One improvement we call compressing find, and the other improvement we call weighted union. In some books, you'll see compressing find, they call it C find, and weighted union, they call W union. You may also see in some books, they call it union by rank. Okay, rank means the size of the tree. So what does compressing find mean? Well, it's a little trick. It says that as I navigate from an internal vertex up to the root, I make any vertices that I find along the way connect directly to the root. So what's going to happen? The tree is gradually going to get flatter, right? It's not going to be as deep. The height is going to go down, which means that the next time around, on average, I'm not going to have to go as far up as I did, before. So we call that compressing find because it reduces the height of the tree. Now, why don't we just make it flat to begin with? Why don't we make it just have one level? And the answer is because that's just extra work up front. So we do that work while we're operating on it anyway. Okay, so that's called compressing find. If I use compressing find, instead of it being E times V, it becomes E log V, which is obviously better. And why does it get smaller? Because our tree, or it's actually not a tree, the trees in our forest are all going to be flatter. They're going to have a lower height. Weighted union says if I have 2 trees and I need to merge one with the other, so don't do it arbitrarily. Always make the smaller one point to the larger one because that will not increase the height overall, right? Everyone get that? So if I have 2 trees, one tree has a height of 10 and the other tree has a height of 3. If I make the size 10 tree point to the root of the size 3, its height is now going to be 11. But if I make the height of the tree with size 3 point to the tree of size 10, then the overall height will still be only 10. So that's a little trick that we use to ensure that the tree doesn't grow. It'll grow in number of vertices, not in terms of height. Now, here's the cool part. If I combine the improvement of option 3 with the improvement of option 4, then what happens is instead of it being E log V, or worse, EV, it goes down to E alpha V. What is alpha? Alpha is the inverse of Ackermann's function. Now, Ackermann's function is a function that grows really quickly. If you've taken 320 or you're taking 320, so you'll actually learn about Ackermann's function. It's a recursive function that is not primitive recursive, very expensive. And alpha grows very slowly. So it's not a constant, but it grows like a constant. So just to elaborate on that, I don't think I have a slide on that, but I'll just write it in the chat. Okay, so let's just open the chat for a second. All right, so to give you some kind of idea of Ackermann's function, right? Is anyone familiar with this log star notation? Have you seen that before?
No.
No, so you're going to see it now. Okay, so what is log without the star? And I'm going to use LG. Okay, LG 16. So that's a warm-up exercise.
4, because 2 to the 4 is
4. Good. And what is LG of, let's say, 256?
8.
8. And what is LG of 65536?
32.
Not 32, but 16, right? 16. Okay, now watch this. Okay, we have 2 to the 2. Okay, that's 4. 2 to the 2 to the 2 is what? 2 to the 4 is 16. And what is 2 to the 2 to the 2 to the 2? Right, everyone see that? Right, that's 2 to the 16th. 2 to the 16th is 65536. Okay, so what is LG star? LG star equals how many 2s to stack to get a number. Okay, so LG star of 65536 equals 4. Everyone get that? Because I needed to stack 4 2s this exponentially, right, to get 65536, which means that what about LG star of 2 to the 65536? What's that going to be equal to? How many 2s are stacked there?
5.
5. Now, can anyone give me an idea of how big a number that is? What trick did I teach you when you're looking at powers of 2? You take the power of 2 and divide it by 3, right? So the rule of thumb is 2 to the n is approximated by 10 to the n divided by 3. Okay, so what does that mean? It means that that number there is like 22,000. All right, so that's a pretty big number. So what we're saying is the log star of that number is not going to be bigger than 5, right? Pretty much any number you are going to encounter in this, the log star of it is going to be 5 or less. So it's not a constant because it does grow. It grows very slowly. So what we're saying here is, yes, it depends on V, but it depends on V so slowly that it's almost like a constant, which means that instead of it being E times V or E times log V, it's almost like plain E, right? So that's pretty good. That's a pretty good improvement. Okay, so here we have an example of union by rank that the term I used learned when I was doing this stuff was weighted union, but they're basically the same idea. So the idea is we take the smaller thing and we make it point to the larger one. Everyone see that? Let's just go back here. Sorry, right? Here's the smaller one, the smaller tree. Here's the larger tree. Make the 2 point to the 1. That's what's happening here. Okay, this is plain union. right? Plain union, we don't care, right? So we have a 2 and we have a 0 and a 1. We can make the 1 point to the 2 or the 2 point to the 1. It's arbitrary. But in union by rank, we were careful to make the smaller one point to the large one. How do you define smaller and larger? There are two opinions out there. One opinion says it's the one with the smaller height. That's the one I usually use. And the other one says it's the one with less vertices. Okay, but either way, it should create the effect of having the tree's height grow very slowly. Right, here's the path compression, or what I like to call compressing find or C find. It says that as you go up, right, you make things point directly to the root. So if we are operating on vertex 3, we make vertex 3 point directly to the root. Why do we do that? Again, it's the same goal. We want to get vertices closer to the source because the next time we do a find, it will go more quickly. It helps keep the height of the tree in check. Oh, so I do have something. Yeah, I do have something on Ackerman's function here. So anyone use the books called by Soodkamp, Thomas Soodkamp for 320? Anyone take 320 yet? So this, I think I stole this from Soodkamp. Maybe I took it from someone. No, maybe it's maybe Wikipedia actually. No, it's Soodkamp. I think it's Soodkamp. In any case, all right. So this is what I was just telling you about before, right? So the oh, that by the way, that 4. Okay. All right. So let's go back to our code for Kruskal for a moment, right? So we spent a lot of time talking about this, right? This was just order V. This was either going to be E times V, or E times log V, or E times just plain E if we use the best of both worlds of compressing find and the union by rank. But there's one piece we didn't discuss yet, which is sorting, right? We had this line here. We just called the built-in sort from Python, right? Which sort is that? It's the Tim sort. But let's say we had control over the sort, right? We wrote our own sort instead of relying on the Tim sort. What sort would you use? So is Tim sort, what is the time complexity of Tim sorts? Anyone remember
N
that?
log n.
We didn't do that one in class, but some of you did that as your optional sort. So it's n log n, right? Can we sort better than n log n? Yeah. What kind of sort should we use for that?
Counting sort, radix sort.
All right, so counting sort, where we don't know how many possibilities. We might have a lot of possibilities for the edges. Well, we can use radix sort, which is based on the counting sort, and that will work well provided that the number of digits is small, right? So the number of digits will probably be small. You know, I have 3 digits, 4 digits, right? Just keep in mind that if it's a floating point number, it stops working so well. If it's just 1 decimal place, you just multiply everything by 10, and then you can use a counting sort with the radix sort, right? So that's what this slide is about here. Let's go back to the slide here, right? So we need to sort, and now remember, we're sorting edges. Okay, a lot of students mess this up because generally speaking, everything is on V. So we say, okay, it's V log V, it's V squared, it's whatever. But we're sorting the edges. So our sorting is going to be E log E unless we are able to use, let's say, a radix sort, which can do E, or bucket sort on the average case. All right. Now here's an interesting observation. E log E is equal to E log V squared. Why is that true, by the way? Elmo, I'm going to come back to you. Why is that true? What did you say before? You said that V squared dominates, right? So yeah. E is bounded above by V squared, all right? So that's why this is bounded above by this. Now we have a rule. The log of the power of something is the same as the power of something times the log, right? So the 2 comes down over here. And so E times O of E log V squared is the same as E log V. Okay, that may not have been obvious. Okay, may not be obvious, but it is. It's not obvious, but it's true. Okay. All right, we have another algorithm here, okay? What's the algorithm called? Called the max flow problem. So the first thing I want to say about the max flow problem is it's different than pretty much all the other graph algorithms we had before. Why do I say that? What is the the graph algorithms that we've done so far? So let's say single source shortest path, all pair shortest path, single source, single destination. What other ones did we have? Today we had minimum spanning tree, right? 2 versions of minimum spanning tree. All right. So are those minimization problems or maximization problems? We try to minimize something or maximize something?
Minimization problems.
They're all minimization problems. So max flow is different in that it's a maximization problem. In this case, the cost of the edges isn't really a cost. It's a good thing. It represents a flow, right? It's how much water, or it could be oil or internet traffic, can be sent through a channel, right? Some other terminology, right? We have our starting point. We call that the source. It has an in degree of 0, meaning no water is coming in there. The water all starts from the source. It doesn't come in there. It's like the source is the spring of water, or the water, the well, or whatever the water is coming from. And the sink is the end point. Okay, so all the sink is, all the water is gone. There's nothing going out. There are no further pipes at the sink. That's the end, right? So we want to figure out how much water can we get from the source to the sink per unit time, right? So every minute, every hour, how much water can we get? So here is a picture, right? This picture comes from CLRS, which is Corman, Lizason, Revest, and Shamir. I'm sorry, not Shamir, and Stein. And it's also on the G4G site, right? So this is an example of a water flow system. Okay, let me explain to you how to read this. So this is saying that, for example, every minute, but it could be seconds, it could be hours, 16 gallons of water can flow from this point to that point. 16 gallons per hour, let's say that. Okay, and this is saying per hour sounds a little slow, maybe per minute. Okay, this is saying 13 gallons per minute can go from here to here, right? From 1 to 2 can 10 gallons per minute. This is saying from 2 to 4 gallons per minute. Okay, so that's the way to read this graph. And again, this is a source, which means no water can come in here. It's all starts there, but doesn't come in there. And no water can leave. There are no pipes going out from 5. That's it. That's why it's called the sink. Okay, so the question is, what flow can we have? So before we get to the algorithm itself, which is a little, I warn you, it's a little complicated, the algorithm. Let's just try to understand this a little bit. And in particular, I want you to look at points where, or edges where, the number is different than in the original graph. And I'm going to explain to you why. So can someone identify an edge where the flow on the right is different than the flow on the left? And let's start, it's easier if we start on the right side of the picture.
From 3 to 5, it's 19 instead of 20.
Okay, so from 3 to 5 is 19 instead of 20. So the question is why? Why can we not use the full capacity? And the answer is, well, how much, you can have more water going in to a, coming out of a pipe, like a socket in the pipe, than the water that's coming in, right? So how much water can go into 3? 7 plus 12, right? You can get 7 from this source and 12 from that source. So the maximum that can come out of 3 in any given unit of time is 19, right? That's why this says 19 and this is 20, because it's very nice that it's a very big pipe and you could get 20 gallons through. But if we don't have 20 gallons coming in per minute, we can't get 20 gallons coming out per minute. All right, let's find another one that's different. So let's take this one here. This one says 11, but according to this picture over here, we actually have a capacity of 14. Well, why is it only 11? Well, let's look. So we have 9 coming in this way. And well, it looks like we have a lot that's coming in. So why is it only 14? I'm sorry, why is it only 11?
Because we have 1 going to 1, vertex 1.
Okay, okay, so here's the thing. Where did these 9 gallons per minute come from?
3.
They came from 3, correct. And where did 3 get them from? It didn't
From
start
1
at
and
3. They came from 1, right? So came from 1, yeah? The 9 gallons that the 3 is able to output. Oh, it could also come from here, okay? So the 7 is also inputting here, but we're already using, here's the key. We're already using the 7 and the 12 to funnel into here, right? So it's very nice that we have a 12 and we have a 7, but that is being used to get this 19. So we can't use that twice. You can't use the same water twice. Either it's going one way or it's going the other way. So that means that this 9 is as if it doesn't exist, right? Because once we decide to allocate the 12 gallons here and the 7 gallons there to this pipe, to this 19, we can't use it for something else. It's going one way or the other, right? So the point of the algorithm is the algorithm is going to do all this work for you. I'm just trying to help you understand, how we get from here to here. So the 9 is out of the picture. So what are we left with? Well, we still have 13 coming in, but do we really have 13 coming in? Well, remember, I have 12 coming in and I need that 12. So where's that 12 going to come from? Well, I have 2 choices. I could either get it from 2 or I could get it from 0. So it turns out that the algorithm is going to decide we're going to get 11 from here and we're going to take 1 from here. So 11 plus the 1 will make the 12, right? That's where the 12 comes from. Okay, so what does that leave me?
With 12.
So if I use 11 over here, I use 11 over there, and what else do I have? So this 10 is now irrelevant because I'm only funneling 11 over there. Okay, so what do I have? Well, I have 13 coming in, and one of them is going this way. Oh, I'm only using 12. Okay, just 1 second. So why do we only use 11? So once I say 12, we understand 1 is going here and 11 is going there. Why? Okay. Yeah, take a look at this. Why am I limiting myself to 11 instead of 14? It's not because I don't have enough water coming in. What's the problem? Look to the right. What pipes do I have going out? What happens? Anyone here in 355? I think I have some of you are in 355, right? So what happens if you send too many data packets to a router?
You have a lot of data loss.
You have data loss, and why do you have them? We drop the packets, right? So if I send too much water in, and I can't handle it, right? Because I only have 7 going out and 4 going out, I'm going to either get water loss or maybe a pipe will explode, right? Water main break. Okay, so again, I only have 11 going out. So I can only have 11 going in. Otherwise, we got a problem. So that's why this is 11. And if I can only have 1 going here, so that's why I only have 12 here. The reason I have 12 here is not because I only had 13. I didn't have enough. I had more water than I needed, right? But I can't have more going in than I can go out. So I can only have 11 here and 1 here. So the total I can take in number 2 is 12, right? So that's the, so you understand what we're trying to do with the code. And the important idea here is something called a residual graph. All right, so you have something called a residual graph. We call this algorithm Ford-Fulkerson whatever this is, looks like it's Java code this time. All right, so it's called a residual graph. Originally, the residual graph is the same as the graph itself, so it's a copy of the graph. Now remember, this is not an adjacency matrix now. This is a cost matrix, except it's not really a cost matrix because the cost is good in this case. So it's like the flow matrix, if you want. And look what happens to the residual matrix. Okay, so the residual matrix goes, gets reduced as we use some of the flow, right? So anytime, right, I'm not going through the whole algorithm here, but I'm going through sort of the most important parts, okay? It's a little cumbersome. And the good news is you're not going to need to know the details of this on the exam, but just so you understand the basic idea. So what we're saying is when we use some flow, we have now used up some of that particular edge because the edge represents capacity. So we have to reduce the flow, but the residual graph in the other direction is saying we now have more flow coming out, right? So this is saying I have less flow available to go in, but more flow that is now coming out. So that's what's happening. This is sort of the guts of the algorithm. And the max flow, what is the max flow? It's how much flow is actually, getting to the what do you call it, at the end of the sink, right? Because that's what we really want to know, right? The goal of this forward focus algorithm or the max flow problem is to figure out how much flow can actually go through the whole network, right? So of whatever we have at the starting point, we may have 100 gallons per minute available at the starting point, but the real question is what do we get at the source, right? With all the pipes we have, and again, that's true with network traffic. So, we have a starting point, we have a bunch of wires out there, different channels that the internet traffic can take, but we want to know how much can get to the endpoint. You can do this with traffic, right? With cars, right? I have a few different highways available to me, but the highways can only handle so much each, certain amount of cars per minute can move along, right? So we look at all that. All right, so if we look at the code, right? We have a BFS going on here, right? So the main loop requires a BFS. How long does BFS take? So that you should remember at this point, right? Using an adjacency matrix, it's V squared. Using an adjacency table, adjacency list, it's V plus E. And then the number of iterations is O of VE. Okay, so it's O of VE. So O of VE times this is either V cubed E or V squared E plus E squared, which the bigger, the more dominant term here is OVE squared. Okay. Last, I think this is our last algorithm for today. Yeah, is a min cut. Okay, and we're going to have another example of a randomized algorithm. And the interesting thing about this randomized algorithm is it was come up by someone named Karger. Okay, I never met Karger, but he was my friend, my good friend's classmate in elementary school. And then he moved away and he went to Harvard, and then he got his PhD from Stanford, and now he's a professor at MIT. I'll tell you what he does, which is interesting in a moment, but he has an algorithm named after him. He might have several algorithms named after him, but this is one of them. It's considered, like, I think, the best algorithm for this particular problem. It's a randomized algorithm. So we're going to see what that is in a moment. But you know what he does, among other things? He algorithmically analyzes like social media data, Facebook data, and so on. That's like a whole new subcategory of computer science. All right, so what is a min cut? A min cut is a way of removing edges to break the graph into two parts. Okay, why would you want to do that? So
Maybe you wanna...
can you come up with a real life scenario where you want to break the graph into two parts?
Maybe you want to break the water system into two systems.
Okay, so let's say you are a enemy of the United States of America, and you want to break the water system so that the water which is here is not going to get there. So how do you do that, right? So one thing would be to find the water tank and just blow that up, Another thing would be to, separate. Or let's say, you're creating two countries, right? You have one big country and you're breaking it up. So how do you break it up? So that's called the min cut problem. And the question is, how do you algorithmically find the smallest number of edges that you need to, chop in order to disconnect the graph, disconnect the system? All right. So it turns out that there is a relationship between the min cut and the max flow, right? Because what is the max flow? It's how much the min cut can, represents, how much flow is going through there. All right, so here's our randomized algorithm. Okay, our randomized algorithm starts with something called a contracted graph. Okay, we're going to call that CG. And the copy of the graph, all right, we take two vertices. How do we pick the two vertices? Pick them at random. So you pick an edge and we look at the two vertices and we say, let's combine the two vertices in the edge into a single vertex. Okay, so watch this. Okay, we randomly picked a vertex. Okay, so we chose A at random. And what happens when we choose A at random? Well, the two endpoints of A need to get combined, right? So that's what's happening here. The 0 and the 1 get combined. Well, if the 0 and the 1 gets combined, then what happens to edge D? Well, the edge D will need to go where 1 is now. So it becomes this round edge, but it's basically just an edge, right? Our next one at random, again, we use a random number generator to pick a vertex. We pick a D. So we get rid of D. Now, what are its endpoints? 0, 1, and 3. So the 0, 1, and 3 all combine. And that's going to be a problem for the C. So the C is between 0, 1, and 3. So now that edge is going to be a self edge, a loop. And the E gets combined. So the E is going to go from the 0, 1, 3 to the 2. And that's what you see over here. Okay, the B is also going to change, right? So that's going to go from the 0, 1, 3 to the 2, and that's what you see here. All right. Now, when do we stop, right? So we keep deleting these things here. When we only have two vertices left in our contracting graph, then we have a min cut. Okay, because basically we're saying these are the two components. All right. So it's sort of like the opposite of minimum spanning tree in a certain sense. Right. So we have two components, so that's our min cut. All right. So our min cut was we had picked the A and we picked the D. And as a result of that, we now are left with the two pieces. So that's our min cut. Okay. So that's that. Okay. So the more important algorithms for today, in terms of, from my perspective, in terms of an exam, is the minimum spanning tree. Okay, minimum spanning tree is a classic algorithms problem. It illustrates greedy algorithms. It also illustrates the importance of sorting algorithms. It illustrates the importance of different data structures. So that's the kind of thing I tend to focus on more. I have asked a question in the past. I think I told you this. Give me some algorithms from a course that begin with the letter K. So you now have two more examples for that if I were to ask such a question, right? You have Karger's algorithm and you have Kruskal's algorithm. So K happens to have a lot of names. That's why I picked the K in the past. Okay, so we have 30 minutes left. I did promise you that I would devote some class time to working on assignment 4 with you. Okay, I'm assuming that people are doing okay with assignment 5. So I need a volunteer, someone who has, let's say, their hash tables or their trees working, but needs help with the infrastructure. Okay, by infrastructure, I mean, the timings and, calling them. So calling them from the loop, not just, individually. So do we have a volunteer who's in a sort of a good position for that? Or if you did it already and you want to show off your code, you could do that too. Can you hear me? Can anyone hear me?
Yes, I can hear you.
Yeah, we can hear you, but there was some like weird noise from I don't know where.
Someone is vacuuming upstairs. I don't know. Do you hear a vacuum cleaner or?
Yeah, something like that.
Oh, sorry about that. Okay. I'll close the door.
No.
I don't know much that, but, okay. So again, we're looking for a volunteer, someone who coded that, say, the hash structures, but needs help putting it together. Or I guess I'll take whatever I can get. So beggars can't be choosers. So if I'm begging, of course.
Professor, I can do the volunteer, but the thing is, like, I think majority of us have the problem with the cuckoo hash and the double hash instead of the infrastructure.
You have a problem with which hash?
Cuckoo hash. For me, I have a problem with
All
cuckoo
right.
hash.
And what was the other one you said?
The double hash.
All right. So let's start with that. So if you want to start with that, that's what you're the one volunteering. So we'll give you the help, and everyone, most people will benefit as well. So let me enable the screen sharing.
One second.
You said the double hash?
Yeah, the double hash of a problem is like
Okay, that's
when
fine. You're talking about the build or the
I'm
or
not
the
sure.
search?
I'm not sure like which part I have a problem. So
Okay.
you tell us to set the size of when we build the double hash to the size of the array input.
Yeah, you can make it bigger than that. Otherwise, it's going to
Yeah, it's run out of space to find
you're
the.
going to run out of. I mean, there will be space, but if you don't have the perfect hash function, you'll never find space. So you can make it bigger if you need to. Excuse me. All right, so let's start with the double, and then we'll go to the cuckoo.
Yeah, I was testing the double, and I seems like. Wait, doesn't have problem this time. It was having problem like when I try to search the double. It's like can't find some.
Did you make it bigger?
Yeah, make it bigger, then it works. Like I
Okay,
make it
so
like
make it bigger. That's okay. Don't make it huge, but make it bigger.
I made it like 5 times bigger. Is that okay?
Okay, that's fine. That's fine.
Okay, then like I found some resource to build the cuckoo hash insert.
Okay,
but
all right.
cannot
So
find
where's
any-
your main build for the cuckoo? Let's just work our way in. So the starting point for the cuckoo.
right here?
No, build cuckoo
Oh
hash.
yeah,
That
right
one.
here.
Build cuckoo hash. Okay, so let's walk through the code there. So you're making the size of the data that you're passing in. That's good. Your hash table, you're making it twice the size.
Yeah, since we have 2 trials, right?
Okay. Wait, so what are you doing there?
When let me think. I think I got the code.
Okay, so so let's look at your loop there, 154 to 155. So you're doing a cuckoo insert. So you're taking,
function.
okay, what is datas of 1? Data of 1 is the key, right?
Yeah, the first key, and then the.
Okay, so why are you starting with 1 and not 0?
Which line you talking about?
Line 155.
That's data I instead of 1.
That's an I?
Yeah, that's a 9.
Oh, that makes sense. Okay, and what are the next parameters? So the 0, 0, what is that?
Let me look into it. That's the count. Wait, that's the table number.
Okay, what is the table number?
Table number is basically like the hash We have two tables, so it's hash table 0 and hash table
You have
1.
two hash tables?
Yeah, isn't that how cuckoo hash works?
Well, you're moving it to somewhere else within, right?
Wait, I thought cuckoo hash is like
Let's
Yeah.
look at the code.
right here, right? We have two set of tables, like when we
Okay, all
wanna
right.
find
So
the
this is, I mean, I guess there's another way to implement it. Okay,
Mhm. So
okay,
I
that's fine.
basically-
That's fine. You could use that. Okay, let's work with this. All right. All right, so you're doing cuckoo insert, and what is hash table is the data structure that holds the two tables?
Yes.
Fine. Okay,
You wanna put it by the side so we can have idea.
well, what are you doing there?
Like I wanna put the code
Oh, okay, fine.
let me see, what's the. Yeah, basically implemented based on the. Wait. Yeah, just got the idea from this, I think.
Okay, fine. Okay, so you're doing the cuckoo insert. All right, so. All right, so tell me what your problem is.
Like I can't find any resource that have like cuckoo search, so I have the build. I'm not sure like what's the proper way to search it to check like whether my build is correct.
Oh, so after you build it, you want to find it? Is that what you're saying?
Yeah, search it basically like.
Okay, so the way you want to search it is basically the way you put it in.
Yeah, okay, but I was
So
trying to do it.
how did you find it in the, how did you find the place for it? So you need to call the hash function. So what hash function did you use to insert?
Okay, just basically cuckoo insert.
Well, that's just calling cuckoo insert. So in the cuckoo insert, how did you find out where it is, right? So what you need to do,
Mhm.
you basically need to go through that whole, you're doing the same thing effectively, right?
Yeah, but the thing is like I did the thing for double hash, but things like for the cuckoo hash, it's kind of recursive, I think, right? No, it's just calling the function
Is
multiple
it
times.
recursive?
No, it's not really recursive. I think.
Well, it is, no, it's
Yeah,
called
it is
cuckoo
right,
insert.
right here.
Okay, but basically you want to call that same code. You're calling the same code, right? As the insert, except you're not actually changing anything.
Yeah,
So
I'm
in
kinda-
line 172, you would not be doing line 172.
Yeah, that's
So
why I'm kinda-
don't erase line one. That's the cuckoo insert. So first of all, what happens when you print the cuckoo hash? Does it look like, can you see where the data is?
You want me to
Have you
print
tried
it?
that? So first of all, you need to call these things outside of, not from your main, right? So if you want, you can take all the code in your main and just move that into another function. And you could call it run trials or something like that. So refactor that.
Refactor. Run
Trials. Okay. Now what you want to do is you want to call instead of run trials, just call your, build your cuckoo hash.
hash.
And you need to give it the data. So find a line that makes data.
I think it's random list.
Do you have a line for that, or it's very simple? Let's go pseudo random list, fine.
Yeah.
Okay. So, and does it return the cuckoo hash?
Yeah, it does, I think. Wait.
Build cuckoo hash, go up. Okay, does it return something?
Oh, I think it didn't.
So
Oh,
how do
it should
you need to return something, right?
return data
It's
something.
gonna be a hash table, right? Not data.
Oh,
So
yeah,
data
hash
is the
table.
input. Okay, so grab that, and so when you call it, grab that back.
Results.
Okay, and print the result. So it's a two-dimensional list, right? So it's two lists.
Oh, yeah, it should be, wait, pseudo random list. What is the end?
So that
Oh, I think that's the,
you need to pass in the size. So pass in 100, or you don't even need 100. Make it small. Make it 10. Might be too small, but we'll try it. Okay, so it looks like everything is empty. Can you do this? Create a variable for pseudo random list. Let's make sure that that works. So refactor that out and make it 20. And create a variable for that. So you can call that data.
list.
And pass the data in.
Pass the data in.
You need to pass the data to the cuckoo hash. And fine, you're going to print the data. Okay, good. Okay, so and you made it unsorted, right? Is that unsorted?
Yeah, I think we
Did a
made it.
shuffle?
Yeah, I did. We
Did you do
did
a
shuffle.
shuffle?
Yeah, we did the
Did
shuffle.
Okay, it's still pretty, okay, fine. Okay, so it doesn't look like your cuckoo hash is doing very much, so we need to fix the build.
Yeah,
So let's go to the build and try to understand what it's doing.
I myself don't really understand this, so
Well,
This
we have
sound-
we have to walk through the code.
build cuckoo hash right here.
Okay. So you're initializing it. Okay. Is this the link I gave you, by the way?
I'm not too sure. Let me check your link.
Look at the code that was in the slides, please.
In the slides,
Yeah, go to the slides. It was the lecture.
that's
Yeah.
gonna be the hash one.
Hashing, right?
Hash, I don't think you. Oh, right here.
Can we look at that? That looks like Java. Maybe it's the same thing. Make it big. So this is the same code. Okay. All right. So let's go back to your code. Okay, so we're creating our hash table with two things in it. Each one is initialized to -1. So -1 is going to indicate that there's nothing there. And then we have pause. Okay, so we go through the amount of data that we have, and we insert the data into the first table. Okay, and what's the second variable? What's the CNT represent?
I'm not too sure. It says the count. So like when it reaches the size, we'll return it. Like we will like terminate.
Okay, so I guess we're starting. Let's see, go back to the Geeks for Geeks code.
Which one you want, like C++?
Java is fine.
Yeah.
Okay, so we had
That's
a init
initialization.
table. Okay, so min value is our -1, fine. Okay, that's good. Okay, and where is their insert?
I think basically this, they call it place. I change it to.
Okay, fine, that's fine, okay. So we are iterating over all the items. So we're doing our check, okay? If the count is a size, fine. We do a loop. Where's your loop?
So this one is made for like when we have I trials, but I personally made it like two arrays, so I hard coded, I think, right here.
Oh, if you're having several different,
Yeah, the VER right here, they made it two, so it's basically just two.
okay, fine.
And the key is supposed to be the hash key returning for the hash function, two different hash functions. So I just hard coded right here.
Okay. So we're taking the position of I.
Wait, did I do it right? I'm not too sure. I think maybe I should follow his, I guess.
All right, so we're going over the different versions and yeah, why don't you,
Grab his for
as
loop.
well, you need the if in between, right?
Yeah.
So let's copy those two lines in, even if you want to hard code the value of VER, but because you need to
Yeah,
be able
my-
to exit. You need to be able to exit.
My if
No,
is
no,
here.
before, but you need to do that between the two pauses.
Okay, all right.
Just paste that, don't erase that yet, just paste it over. Oh, you're commenting, okay. Okay, so VER is just two. Why don't you, instead of change, do this. Leave it as VER. Leave it as VER. And right above that, say VER equals 2. So this way, if you get VER again, okay. Now let's change the Java to Python. So you're going to say for I in range VER. And you're going to say pause of what is paused? We have pause.
Yeah, it's to record the position, I think.
Okay, that's the pause array. Okay, fine. Okay, equals hash of I plus 1.
Oh yeah, that's the hash function.
We need the hash function. You have the hash function?
Yeah, only hard coded, so
Where
maybe
is the hash? Where is the hash function?
like I use the number that modular by size and the number divided by size.
Okay, so let's give it a name. Let's try to follow their syntax, because once we deviate,
maybe I should
we could call it my hash, but let's follow the.
So I should define hash function.
Yeah, well, how is it defined there?
Yeah, they have a hash function. So
Okay, so let's follow their example.
my hash.
Paste. Okay, so def hash, we're going to pass in, let's call it function num. Okay, int key, fine, colon, and instead of a switch, we'll use an if statement. Okay, so we'll say if func num equals 1, So we'll return key. And what are you using instead of max n?
Only max, and I'm not too sure that is that, but I divide
Oh,
by the array
that's,
size.
that's, okay, fine. You can
Yeah, they
make,
hard coded to 11.
okay, so let's hard code it, not hard code it, let's just pass in a size, so. Call it, max size or something. I wouldn't call it size because size, you're using it to also mean the number of data elements, so.
Yeah, but that's basically of the number of elements.
Okay, all right, fine.
Yeah, that's what I did for my code or my code.
And you don't need the data types, so you can get rid of the int and the key, the int. Wait, why'd you get rid of that? Undo?
Wanna like do another if statement, right?
Yeah, just do else, or if you want an elif if you prefer. I mean, it should always be one or the other, right?
Yeah, well,
Now they're calling them 1 and 2. Fine.
oh, my second one is he.
I wouldn't use the double slash, by the way. I would use the int key divided by size.
Oh, okay.
Int of the whole thing, key divided by size. And then modulo size. You got an extra parentheses there. Okay, get rid of the rich, and then get rid of that return. And you've got an extra parentheses going on around the int.
Int.
You don't need it. You don't need that. It's extraneous. Okay, so that's your function. Fine. Now go back to the cuckoo insert. Okay. So let's clean up that code there. So you need to pass in the size. You have this size, right?
Where are we?
Stop. So you need to pass in the size because you don't have a constant, right?
Which
Line
one?
179, you need to pass a third parameter to hash.
Oh, right.
Okay, and then you're going to say if hash table of,
Calling now myself, so
what is num?
just a key. I
Num
like
is
to-
your key?
Yeah.
Okay,
Okay.
is there a reason? Can we pass in the, can we call it key? Key is a
Okay.
better name than a num. Let's refactor.
Okay. So we call it.
Because num could be anything, right?
I don't know. I just I feel like it's inserting to the table, so I code it now.
Okay, you can get rid of those parentheses there in line 180. And why is that? And you need to indent the return, right?
Yeah.
Okay. All right, now what happens in line 183? Let's compare 183 with there. So you have hash table, the table num. You have the pos of the table, table ID and table number, the same thing, I guess. Not equals to -1. Okay. So that means that we found something there. You might want to say a comment there, right? Put a
Okay.
comment right there. Normally I like to get rid of the comments, but in this case, I think we need that. So you can put it on the same line if you want.
Yeah, but oh, okay.
If you want, you could say if something else is already there.
That's something else.
Okay, so we are doing dis equals hash table, the table num, the pos, the table num, fine. Next line is hash table, table num, pos, table num equals key. And we do cuckoo insert is place, right? So cuckoo insert dis table num plus 1 mod 2, right? Make that mod ver.
Oh, yeah. Wow,
Okay, and count plus 1 comma. Now, why do we have more parameters there than they do? Because some of our variables are,
yeah, because for
well, we need to
Java,
pass them around. We don't have these class variables or whatever. Okay, fine. That makes sense to me. And we need an else. Why don't you have an else? Where's your else?
I don't know. I probably didn't see that part, I guess.
That's, it looks like an important else.
Hash.
Yeah, because you're basically saying we can never put anything in there, right? Because
Oh.
if nothing is there,
Yeah, seems like that's the reason.
that's a big problem. Okay. All right, you can get rid of lines 172 to 176 at this point. Okay. Fine. Okay, let us run that. Okay, so we have a bunch of stuff. And if everything is going right, that means all those numbers should be in one or the other.
Seems like right, I guess.
So you can count the number of, okay, how many elements do we have? 20?
Let me see. Yeah, 20.
20.
Maybe
So
make it
count the
10.
number of non-zeros, the non-minus ones.
Wait, am I missing one?
You counted 0. Where was that 0 in the data? Oh, 0 was in the data. Look at that.
Oh, yeah,
Okay.
then it's 20, I guess.
Okay. All right. That's good.
But
Okay, so
So-
go back to their code.
mhm.
And do they have their own search?
No, I don't think they have one. That's
They
the problem.
probably. Okay. So the way you want to search is basically the way you insert.
But
So you
Do we
take
need-
your hash table. So go to your search. Go to your search. You're going to take a hash table and you're going to take, instead of num, we're going to call it key. Okay, and you're going to so if need be, you could just copy all the code from the cuckoo insert for now. So we don't break that, because I think that is working now. Okay,
what did I did?
I don't know what you did. All right. I don't think we need the if count equals size. I don't think we need that. And you know what? I don't think we need the vert equals to. Let's go up to the other one. And instead of vert equals 2, you could say vert equals len of the hash table, right? Because the hash table is going to be of size 2. Is that correct? Look up, go up to where you coded it. So hash table is times 2, okay? So your len of hash table is going to, so ver is equal to the len of the hash table. So the less variables we have, the better. Go back down and do that in the search. Okay, so what we're going to need to do is we're going to say we search through the two tables, right? That's in line 190, right? We're going to go through the tables and we're going to look. If it's the key, then we're going to return the position. So the position is, I guess, POSI.
You mean like this return the,
Well, now we're going to actually return the position.
you want to return the position I?
Yeah, so you also need to return, I guess, the table where you found it, right? So we'll return a tuple. So you could say, I guess it's I, comma, positive I,
Comma.
positive I. Okay. If that becomes a problem in your later program, you could just do the positive I, but basically that's the position, right? You're saying the table and
Not really, but actually not really sure about what's the position array is doing though.
well, the position is where in that table it should be,
Like,
right? It's saying where in the table should it be? So
okay.
depending on the table, you're using a different function. So
Okay,
if you
so-
find it, great, then you return. Otherwise, if there's something else there, right? So I think what you need to do is if you're going to need to return the cuckoo search. So in your code, you're going to need to return cuckoo search, search cuckoo hash.
Return here.
Yeah. You're going to say return search cuckoo hash of the displacement.
Displacement.
Okay, you know what? Well, we're just gonna, I think we're just, no, we need to compute the displacement. That's the dis. So in the cuckoo insert, let's go to the cuckoo insert. Go up to the cuckoo insert. What was the first parameter? Is the key?
Yeah, that's the key.
Okay, go back down. So when you called cuckoo insert, you're passing the dis. Oh, because that's the other key. Okay. I think you can just do return search cuckoo hash table.
This.
You know what? Just comment out those lines. Okay, 195 to 201. Just comment all that out. Okay. And you can try running that. Why is that underlined?
Because we don't have a pause in this search. The pause was stored in the
Okay, so you can just you could just say pos equals the hash. No, in that line, So instead of pos of I, you can just say pos equals hash and use that in the next line also. Instead of pos of I. Instead of pos of I in 191.
Return pause.
And in the return also. Okay, So here's what I want you to do.
Mhm.
Okay, now I want you to call the search cuckoo hash for the data. Go down in your little test program there. So you could say for key in datas. Okay, and then call the search cuckoo. You could say index, IDX equals search cuckoo hash table. Now, where did you build the hash table? Oh, result. Result isn't the best name for that. Can we change the name in 250?
Mhm.
You could
Wanted
call it
to-
cuckoo hash equals. Good. And you pass in the key. No, not bracket. Cuckoo hash is your data structure. You're going to pass in the key, separate parameter,
Oh,
comma, key. Okay, and then print the IDX. So it will be a tuple.
next.
Things go well, it should find everything, right?
You want me to comment those out first?
You could leave them so we know what we're dealing with.
Oh, dang, because like we have the size in here. What's the size?
So do we know the size? Do we know the size? What is size? Size is the number of elements?
Number of element, yeah.
Okay, so you could pass in the size if you want to the search cuckoo hash, that's fine. Pass it into the search cuckoo hash. Okay, and you'll pass it in below also. All right, that looks good. I don't see anything that says none. Right, none would be a bad word here.
Hmm.
Okay, that means it found it. So most of the time it finds it in the first one, which is good. In some cases, it needed the second data structure, right?
Oh, this is saying like that's the index for the.
It's the first thing is the table, because you have multiple
Mhm.
tables, and the second one is the index within the table.
Oh, okay, I
Okay,
see.
by the way, in your print, I would also do key comma IDX, just so you can see what's going on. It'll be a little better. So now you see, oh, this time we got a none. That means it couldn't find it. Which may mean we don't have enough tables. It could be that.
Yeah, that's the same problem ring to the double and the quadratic.
So if you need to, you could make more. Yeah, see, look, you see that cycle present rehash? Look up.
Oh, yeah.
Okay, that means so
To run out of space, that's what it's saying.
it's not run out of space. It's saying you need to rehash it. So basically, you would need to have another kind of hash function. So what do they recommend in that situation? Go look at their code. Go down. Where's that cycle code? So what does it say to do? A function has been recursively called max number of times. Stop and declare a cycle. All right, so you could try to expand the size of the data structure or have more tables, but I would make the data structure bigger.
Make the data structure.
Where did you make the data structure initially? Go back up to the build the cuckoo hash.
Maybe time it to 5 or 2.
Wait, but this is saying that it just, what, it can't find a place. That's what it's saying.
Yeah, because it seemed like the negative
Ow.
one wasn't take place, so don't think that's a problem of the. So it should be
So it
looking
means that
for
it means that the hash function is not well distributed. That's what it means. So for the purpose of this assignment, just make that bigger. Okay,
that
so
bigger.
make it times 10, just to get through the assignment.
And so should I
But
multiply the hash table the try
no,
like
no, it's
over
not by 2. No, that's the number of hash functions. 2 is the number of hash functions, right? Yeah,
yeah.
okay. So hold on, but you do need to, but you have to be careful because the size there is just go down wherever you're using the size. See, hold on. You're using size 2 different ways here. Okay, go up. You have to be careful with this. Go up. So, and it might help if you make more specific names, because size means what? Is size the amount of
input
data that you
size.
have? It's not the input size though, right? Because you're multiplying it by 10. So the number, the input size is the len of datas. So if that's your, your table
Maybe
size, then call it
shouldn't
table size.
table size.
But you, no. Well, just, you got to name your things so that you know what they are.
Yeah, because I did the way that size is the input size, so
That's
maybe
fine. But if your hash table is a different size, then you got to call it that. No, that's the number of hash tables. 2 is the number of hash tables. If you want, you can create a variable for that.
okay, maybe
Okay.
table size. Table size, and then data,
Don't do len twice, then use size.
the size. 10.
Yeah. Okay, now instead of 2, I would use number of tables. Create a variable called number of tables.
Tables. Tables.
Num tables is fine. Num tables. You don't need the word up. And use that in line 150. And use that in line 153. And now I need you to be careful because when you're using size in 156, what is that size? How are we using it?
Because originally the
Go into the
number of-
cuckoo insert. Go into the cuckoo insert and see what it's used for.
Hmm.
That's fine. That line is fine. But you have to see what that size is. Is size the length of
I
the table? It's
think-
probably the length of the table. Probably not the amount of data. It's the size of the table. Okay, so you need the size of the table in line 170.
Table size, you mean?
And if you need to pass it in, you pass it in.
Did I call it? Oh, table size. Where should I put it?
You could just change the name of size. Because it doesn't really depend, it's not about the amount of data, it's about the size of the table, right?
Hmm.
Okay, you could try it again. Now it's possible we could still get a cycle here because it's just, luck.
What about this?
So in the search, it's also based on the table size.
Okay. Tables.
So you're gonna need to pass in, I guess, the 10 times.
Okay.
Oh, but you need to pass in the right number. go down. You call it, when you call it, go down. It's not the len of data. It's 10 times the data, right?
Hmm. That's data.
Well, you gotta look at,
Was in the
well, you gotta click,
search.
you gotta click on the error and look at the line. Click on it, click on the blue. So we're looking at hash table of pos. Did you create the hash tables of the right size? Go back up to the build. Looks like they're not big enough. Yeah, that's your problem. Look in line 152. You need to do table size. 152 and 153.
Oh, okay.
And you should probably do that in a loop, by the way. Lines 152, 153 should be in a loop over the number of tables. And then I need to stop because I have another class.
All right.
So instead of those two, you say for, for table in num tables.
Yeah, I got it. Okay. I'm
it.
gonna share the Cuckoo hash with everybody, I think.
All right. Okay,
We'll
great.
work on-
Thank you, Cheng. All right, I gotta run.
Okay, thank you, Professor.
Bye-bye.